In this video, I am going to explain about the packing efficiency in solids. So children, by packing efficiency, we mean how efficiently the space is used in solids. Because solids are very compact and entire space is used in a highly complex manner so that no space is left unoccupied. And this is the meaning of packing efficiency. And children the solids are of different types. It can be cubic solid, it can be FCC, it can be BCC. So different classes of the unit cells. Basically the unit cells, they are having a special type of arrangement of particles, and there is the slightly different property of the solid, of the lattice, due to the efficient way of the packing. However, some are slightly more efficient, some are slightly less efficient. See how is it. Now children, I am going to explain how we can find out the packing efficiency in case of HCP, in case of different type of unit cells. Now see, here I have drawn a unit cell, it is FCC, and see children, this is triangle A, B and C, and here there is the void. Actually you have seen about the void, and so voids actually they provide more efficiency, because what is void? What is the intercellular space carried by any particle? So it is in addition to this. So here the bigger particle, here the smaller particle lies in the void. So triangle A, B and C. So this R and R is the radius of the void, and here it is also R. You may write capital R also depending on the condition. Now so children, see how start. In triangle ABC, AC square. AC square, it is face diagonal. Here AC is face diagonal, and it is represented by letter B, and A is the edge length. This is edge length. So here in this cube, edge length it is represented by A. Edge length is represented by small a. So in triangle ABC, AC square is equal to B square. This is the B face diagonal. This is the face diagonal. AC is face diagonal, and so it is how much it is? B square. So BC square plus AB square, it is equal to AC square. So this BC, it is what? It is nothing but it is edge length, because in cube all the edges are same. So A square plus B square, this is face diagonal, and so it is equal to 2A square, or under root 2A is equal to B. And here, if R is the radius of the sphere, as I have said, R is the radius of sphere. Here just I have mentioned all small r, but if they are bigger, so it is represented by capital R. You will see later on. Then B is equal to 4R. This AC, so this is equal to, see, 1R, 2R, 3R and 4R. Once again, how? B is equal to 4R, 1R, 2R, 3R and 4R. So B is face diagonal is equal to 4 times of the radius, or it is equal to under root 2A, or A is equal to 4R upon under root 2, or 2 root 2R. Now, in CCP, cubic closed packing, 4 spheres are present. This thing, 4 spheres. The rank CCP cubic closed packing. So, volume of 4 spheres, because 4 spheres are present in CCP. So 4 into 4 by 3 pi r cube. The volume of any sphere, it is 4 by 3 pi r cube. So or AQ is equal to under root 2 r power 3 or cube. So packing efficiency, children, we can find out. Efficiency can be find out by volume occupied by 4 spheres. This area, this unit cell has total volume of 4 spheres. So a volume of 4 spheres upon total volume of the unit cell, because very small space in the unit cell is left which is unoccupied, and they are so meager, they are so minute that they cannot be used to find out. So packing efficiency, it is equal to volume occupied by 4 spheres. 4 spheres present in the unit cell upon total volume of unit cell into 100. And so we find out like this. So children, at last we can write, so packing efficiency in case of FCC, it is 4 into 4 upon 3 pi r cube. This is what? This is the actual volume occupied by the 4 spheres present in the unit cells upon total volume of this unit cell into 100. So it comes out to be 74%. So this is the value, this is the efficiency. Meaning in case of FCC, in case of CCP, only 74% of the space is used. And so you can imagine how much it is unoccupied. It is 26% to 26% of space is left unoccupied, and so children know this is responsible for the dislocation of particles in any solid. Now in this I am going to explain more points about the packing efficiency in case of cubic system or simple cube. So children, for the simplicity to have the less time, I have drawn a simple cube, and in a simple cube there is the presence of particles at the corners. You know, simple cube or simply cubic system, particles are present at the 8 corners. And now 8 corners, 8 into value is 1 by 8. So what? It is equal to 1. So in a simple cube, number of particles is equal to 1. This thing you know already. Second, this edge length, edge in the BCC. So edge length in a simple cube, it is represented as A, and all the arms they are A, they are equal, they are similar. Now see volume. First we see volume of unit cell, you know, AQ or LQ, so it is AQ and it is 2R. This R, this is 1R, this is other one. So what we can say children, here A is equal to 2R. Edge length is equal to twice of the radius of the particle. So it is 2R cube is equal to 8R cube. As simple cube has one atom, just here I have verified. So one atom, so volume occupied is equal to 4 by 3 pi r cube. So as it is only one, in this cube there is only one particle, so it is 4 by 3 pi r cube. So packing efficiency as we have seen previously. So volume of one atom upon volume of unit cell into 100. So volume of one atom, you know, here this 4 by 3 pi r cube upon volume of unit cell, here volume of unit cell 8 r cube into 100. So pi upon 6 into 100. So it comes out to be 52.4%. So children, this is the condition. So what we can say, FCC is most efficient and it is 52.4%. So this is all about the packing efficiency in case of solids. FCC, BCC, all are same, and this is the cubic has the lowest, it is 52.7.